So if I miss a lone pair or something, let me know. Just type it in the chat because I'm kind of blind. All righty, Chemistry 3101. We finished up Chapter 6 yesterday, and I posted these practice problems. These come straight out of Klein, and there's just a bunch of arrows that we need to push here. And so it's just getting a little practice on the patterns that we learned last class. So those were nucleophilic attack, loss of leaving group, proton transfer, and carbocation or hydride rearrangement. And so really these problems are nothing more than practicing drawing each one of those patterns and getting some practice in recognizing them. So let's take a look at the first one. You can see that we have a hydroxide. Now keep in mind that hydroxide is not only a strong base, but it's a very powerful nucleophile. And you can see that we formed a bond here between this oxygen from the hydroxide and this carbon in the aromatic ring, which ceases to be aromatic at this point. It's not aromatic here. So could anybody tell me what would the pattern be that you see here in this problem? Anybody? Is it a nucleophilic attack, loss of leaving group, proton transfer, rearrangement? Thanks, Katana. Yeah, this would be a nucleophilic attack. So we put in our electrons like this, and we have the nucleophilic attack. But you notice that if you were to just draw this arrow like this, then this carbon would exceed the octet rule, and we can't do that. And you see that there's been some other bonds moved. You see that they moved this pi bond over here. This pi bond has been moved over here, and this pi bond has been broken. And these pair of electrons, or this pair of electrons, has ended up on the oxygen because it started out with 2 lone pairs, and now it has 3 lone pairs over here. So 1, 2, 3, 4, 5, 6, 3, 4, 5, 6. Anyhow, there we go. So we have a nucleophilic attack in the first step. Okay, so the second step, you can see that it says minus CH3 SO3 minus. So that means we're losing something. So anybody want to take a guess at what kind of step we're looking at here? And it's not a trick question or anything. What kind of pattern are we seeing here? Yeah, thanks, Kiana. It's a loss of leaving group, isn't it? Loss of leaving group. And we have to draw quite a few arrows in order to make this leaving group leave. We're going to have to reform our nitro group. So we're going to have to make a pi bond here. Then we're going to have to move this pair of electrons here in the ring, move this pair of electrons over here, and then we're going to break this bond, and we're going to lose, oops, I'm losing the wrong group. We're going to lose our sulfonic acid. Or we would call that a methyl sulfonate is what that would be called. Anyhow, the name's not important, but that's our loss of leaving group. And you can see we had to draw a total of 4 curved arrows in order to lose that leaving group. So the last one is kind of silly, the way they've drawn the molecule, because you need to redraw it in order to draw this proton transfer. So there's a proton transfer happening here. And I'm just going to redraw the molecule, and you'll see why. And you'd know if you did the problem. So you have to redraw and show the bond between the oxygen and the hydrogen. Okay, so our base now, and let me put in all the lone pairs on the hydroxide. Our base is going to pull this proton off of the OH group here, and we end up with, we call this a phenoxide here. It's not an alkoxide, it's a phenoxide. All right. So if you were to try to do this, and don't do this, but if you tried to do something like this, like, oh, I'll pull this, and then I'll just make an imaginary, don't do that. Okay, just redraw the compound. It takes a few seconds to redraw the compound and draw proper arrows like that. All right, there we go. So we had a nucleophilic attack, loss of leaving group, and a proton transfer. Let's move on from there. Let's try this one. And again, it starts here on the top left, and it goes like this. So that's the sequence of events in this reaction. You can see that we go from having 2 rings to only having 1 ring down here. So we must have to break a ring at some point. And you can see that we're starting out with a nitrogen that has no hydrogen attached to one that has a hydrogen attached. Therefore, what kind of step is taking place here? Anybody? Yeah, it's definitely a proton transfer, isn't it? Absolutely. So let's draw the proton transfer, right? The nitrogen is taking the proton from the hydronium ion. And so we're going to start with the tail of our arrow on the nitrogen, and then it's going to attack that hydrogen. And then we have to take that pair of electrons and put it back on the oxygen to make water, right? When H3O plus hydronium loses a proton, what does it become? It becomes water. And so you can see that we've got a very strong dipole here, right? We have a dipole going in this direction, which renders this carbon is very electrophilic. So electrophilic, okay, very electrophilic. And you can see that water, even though it's a poor nucleophile, it's a weak nucleophile, since this carbon is so electrophilic, we could put very electrophilic that the water molecule is going to attack at that carbon. So we have a nucleophilic attack occurring here. That would give this carbon 4 bonds. And you can see we need to put a lone pair on the nitrogen. So we're going to break this pi bond and put the pair of electrons on the nitrogen. So this would be a nucleophilic attack. All right, let's take a look at the next one. We're going from the oxygen having 2 protons to only having 1 proton. Therefore, what are we looking at? Anybody? We're looking at another proton transfer, aren't we? So water is going to behave as our base, right? It's going to attack this proton. And if you're like, well, could it be this proton? Yes, it doesn't matter. So we're going to take that proton and we're going to take the pair of electrons in that bond and put them as a lone pair on the oxygen. So again, this was another proton transfer. Next step, you can see we're transferring a proton onto the nitrogen. So the nitrogen starts out with 1 proton. Now it has 2. So we start with the tail of our arrow on our nitrogen. We grab that proton and we put these electrons on here to reform water. There we go. And then in the next step, you can see that the ring is actually opening up. And so this is an intramolecular loss of leaving group, right? So I didn't write proton transfer here. So now we have a loss of leaving group, but the leaving group is inside the molecule. And when the bond breaks, it's still tethered to the molecule. So what's going to happen here? How do we lose this leaving group? You can see that we have to break this bond, right? That bond must be broken. And we're going to take that pair of electrons and put them on the nitrogen. But when we do that, that would leave the carbon with a positive charge. And so we take this pair of electrons from the oxygen and we make this pi bond here. So it's an intramolecular instead of inter between two things. It's an intramolecular loss of leaving group is what you would call that. And then the last one is just another proton transfer. So the water is going to act as a base. It's going to take this proton and you're going to put the pair of electrons down here. And there you have it, a proton transfer. Any questions about any of those steps in that reaction? Did everybody get that one when they tried it at home last night? Or maybe at 4 o'clock this morning or something like that? Awesome. Awesome. There you go. All right, good. Well, let's move on from there. Let's take a look at this one. This one's a little more challenging, I think, is quite a bit more challenging. So we can see that we have a proton that's being transferred here. So we're losing this proton, right, because it's not here. And then you can see that there's a whole bunch of bonds changing place here. So there's a couple of things happening here at once, okay, in this first step. So if we put in the lone pairs on our hydroxide ion like this, okay, you can see that this proton is being removed, right? Hydroxide is a strong base. And then we're going to take the pair of electrons between the nitrogen and hydrogen and make a pi bond here. But that would exceed the octet rule for the nitrogen, the next nitrogen. And so we're going to make a pi bond. Oops, where's my red pen? We're going to make a pi bond, excuse me, here. And that would exceed the octet rule for this carbon. And so this bond breaks. And so you have a proton transfer occurring here, but then you have a loss of a leaving group occurring here to make that alkoxide. So once you have the alkoxide in place, so let me just kind of center this here. Okay, now we need to form a triple bond somehow, and we need to lose chlorine. So you can see that we're forming a double bond, right, between the oxygen and this carbon. And so that's where this mechanism is going to start. We'll put in our lone pairs here. We need to form a pi bond here. But what's going to happen is you can't exceed the octet rule of this carbon. And so you have to make a triple bond here. And then that would cause nitrogen to leave as a gas and chloride to leave as an ion. And so those are all the curved arrows here. Now it says here, just draw the curved arrows. It doesn't say to identify them or anything like that. But you can see that you're losing nitrogen and you're losing Cl minus. And so these things here, these would be loss of leaving group. There's 2 of them occurring simultaneously. And I guess this one here, you could technically call it a nucleophilic attack kind of thing. No, actually, I wouldn't call it that. I would just call that a resonance arrow. But we have a loss of leaving group because we're losing these two guys here. Remember that N2 is a gas, right? N2 is going to go up the smokestack. So remember that nitrogen is a gas. So based on Le Chatelier's principle, this is definitely an irreversible reaction, isn't it? Right? It's just going to go in one direction. All right. And again, that one's pretty challenging. This one here is the last one. I think I took this from the challenge problems or something. So this one is a very complex problem. So let's see here what's going on in the first step. You can see that we're forming a bond between oxygen and carbon here. And so this must be a nucleophilic attack. I don't know what he's got against lone pairs on his hydroxides, but anyhow, so we have a nucleophilic attack like this, okay, to make that alkoxide. And then we have to lose this whole carboxyl group here. So you can see that we're doing a loss of leaving group. So we're going to lose OH minus, and then we're also going to lose kind of, we're going to lose a hydroxide, and we're going to lose, this is called acetic acid here. So let me just see here. I didn't even try this one before class. So what's going to happen is we're going to move this pair of electrons down here to make the double bond, right? Well, maybe they just have the hydroxide as a reagent here. Am I missing something here? Because that would not make sense. Oh no, you must lose the hydroxide too. Oh, I see what's going on. So here, we're going to end up losing. I see what's happening. This oxygen with this negative charge is going to take this proton here. That's what's going on. So when it does that, it ends up forming this double bond, right? This double bond here. And then you end up losing the acetate ion like this. Yes. So we end up losing the acetate, and so we end up losing the acetate like that. Oh, I see. It must be these electrons. So the first arrow, it must be this pair of electrons because that would break this bond. I've got, there we go. So those are the curved arrows. Like I said, this is a challenge problem. I wouldn't ask you this one. Anyhow, so in the last step, you just have a proton transfer. I could definitely ask you this one here, where we get something that looks like this. So we're just going to deprotonate here. And there you go. So that's going to be, again, I would say this step would be very, very challenging step. So don't worry about me asking you anything that complex, okay? Like I said, I took this from the challenge problems just to give you an extra problem to work on. But there we go. So what would the name of the second step be? The second step is a rearrangement. It's just a rearrangement that we never looked at, okay? So it wouldn't fall under the umbrella of carbocation rearrangement, or sorry, it wouldn't fall under the umbrella of methyl or hydrogen shift. It's just a different kind of rearrangement. Yeah, something that we've never covered before, but you just kind of follow the arrows to get to the final product. But again, this would be a challenge problem, so I wouldn't stress about me asking you any kind of, this is an intramolecular rearrangement. There you go. Okay, so let's see here. So there are some, like, I'm sure you've all seen the challenge problems in the textbook, and sometimes I assign those, sometimes I don't.